Um, Next topic that we are going to cover is the classification and application of metals. Right. So most well, a lot of metals, a lot of engineering metals that we use are mainly steel based, right? So steel counts for like most of the metals that we use in engineering, right? The reason for that is because steel is quite cheap, quite easy to produce. It's got quite good properties, but it doesn't have like the best properties, right? For specific application. Steel have like one of the worst thing about steel is that the density of steel is quite high, right? So it weighs quite a lot. So sometimes we need other materials with comparable strength to steel, but better in every other ways, right? Like lighter or more corrosion resistance, etc. Okay. So for engineering metals, uh, engineering metals can be divided into two large groups, right? The first one is called ferrous metals. The second one is called non-ferrous metals. Ferrous metals refer to alloys of iron, right? So you would get steels and cast iron, like etc. Metals with iron as their main component. The other group is non-ferrous alloys, non-ferrous metals. Other metals other alloys with other materials are apart from iron as their main components. Today we're going to look at non-ferrous metal first. Okay, so the first non-ferrous metal that we're going to look at is the copper and copper alloys. Right? Copper and copper-based alloys have been around for a long time. In fact, copper has been one of the first metals that humans have been using. If you look at history, right? So you start off with the Stone Age, right? And next, after Stone Age, we get Bronze Age. After Bronze Age, we get Iron Age. The name of these ages refer to the material that we are using as human being, right? The materials we are using in our lives at those times. So in the Stone Age, we are using stone as our tools, as our weapons, right? In the Bronze Age, we start to use bronze as our tools. And what is bronze? Bronze is actually an alloy of copper and tin. Right? So usually, where you would find copper, you would probably find a small amount of tin in that area as well. Because pure copper is really soft and not very useful at all. So when you mix together, as early human did, they accidentally mix copper and tin together to form a bronze, a new alloy which is stronger. So in the Bronze Age, humans start to use bronze, right? And in Europe, the main source of bronze comes from area around Cyprus, right? So, in fact, the name Cyprus comes from the Greek root of kupro, which means copper, right? Kupriot, right, which means copper. So basically, Cyprus was the island of copper, the main source of copper in Europe. So you can see that during that time, during the Bronze Age, up to the uh, Hellenic civilization, that area of the world is like dominating Europe because it's got the source of copper that it can use as tools and weapons and can make lives easier and can dominate other areas. The same happened in China in the Yangtze River Basin, and you start to get like bronze, and also in the south of China, right? Okay, copper and copper alloys have very good uh, properties. Like it's got good, relatively good strength. Um, it's got good corrosion resistant. It's been around for quite a long time. It's been around since antiquities. Uh, Pure copper or unalloyed copper is very soft and ductile, um, and it is not very useful, right? Because it cannot be shaped into the shape that you want quite easily. It cannot be machined quite easily because it is too ductile, right? It can be cold work. Cold work in this case means to shape into the shape that you want at low temperature. And as you are doing the cold working, you are increasing the strength of that alloys as well, right? Cold working is the opposite of hot working. Hot working is when you are shaping something at higher temperature, and by doing hot working, you are shaping it, but you are not increasing its strength. Whereas when you are doing it uh, at lower temperature, you're cold working, you're shaping it and increase the strength at the same time. Because as you are cold working a workpiece, you are introducing more and more dislocation in that workpiece, making it stronger. Right? We will talk about cold working and hot working after the midterm, right? After um, in the manufacturing session. Okay, copper is very resistant to corrosion, um, especially in seawater. Right? So, for example, steel is very bad at withstanding seawater. It will corrode really quickly in seawater. Even stainless steel can be corroded in seawater, right? But copper alloys like brass is very good against seawater. You don't get any pitting corrosion in brass or bronze. Okay, um, brass is an alloy of copper with zinc. Usually, you would have this yellowish goldish color, like it looks really like shiny yellowish, like just like gold. Depending on the amount of zinc that you put in. Right? If you have just a little bit of zinc, it will look more sort of reddish, yellowish gold color. But if you have more zinc, it will more you would have more duller yellowish color. Right? The zinc content can vary from a few percent up to about 40%. Usually, we are we are using brass of usually maybe 30% zinc, 20% zinc, right? But if we want to use the brass in corrosion application, right, corrosion resistant application, we usually have to limit the amount of zinc down to about 15%. Um, Bronze is another alloy of copper, usually tin, right? But you can also have aluminum bronze. You can have silicon bronze when you alloy copper with aluminum or silicon, for example. Tin, tin, tin bronze or most bronzes are usually stronger than brass, and also have good corrosion resistance, just like brass. Right? So usually bronze are stronger than brass, same corrosion resistance, but a little bit more expensive, right? Because zinc is very cheap. Therefore, when you combine copper and zinc together, you get a cheaper alloy with good enough properties, good enough strength, good corrosion resistance, but the strength is not as high as bronze. When you're combining copper with aluminum or tin or silicon, these materials are a bit more expensive than zinc. Therefore, that makes bronze a little bit more expensive than bronze. Bronze is a little bit more expensive than brass. Next is the aluminum alloys. Aluminum alloys is really aluminum and aluminum alloys are famous for its low density, right? The density of about 2.7 gram per centimeter cube compared to 7.9 gram per centimeter cube for steel, right? It's got about maybe more or less about 1/3 of the density of steel, right? So it is lighter, right? Aluminum has high electrical and thermal conductivities. If you look at the overhead power line, most of those power lines are made from aluminum, right? The electrical conductivity of aluminum is is about the same as that of copper. It's very good, right? But because it is lighter than copper, it has been chosen to be used as electrical power line, the high voltage electrical power line that you see in the countryside, right? Those are made from aluminum. Why? Why don't they choose like copper? When copper maybe edges it just a little bit in terms of conductivity. But why do they choose aluminum and they don't choose copper? Aluminum is a bit more expensive than copper, but the the aluminum is chosen to be used as high power, high voltage electrical power line is because of the low density. Because remember, you have to use quite thick cable, right? And the weight of that cable can be quite high, right? So if you're using heavier and denser material like copper, you would have high weights of the cable. So your pylons have to be closer together, right? To distribute the weights better, right? So you have closer pylons, you have cable made from copper. But because aluminum is lighter, has lower density, the density of copper is about about the same as density of steel, right? A bit higher than steel, but about the same, somewhere around 8 grams per centimeter cube, right? Aluminum is a lot lighter, so you can have longer distance between the pylons. Right? So you can have longer distance. That means you have less number of pylons that you have to construct. Therefore, you save money there. Right? So in the long run, aluminum construction won out. The conductivities of aluminum is not that far behind copper, so you use aluminum in this case, not just in the power line, but in the substation, in the bus bar, etc. Aluminum is very good at resisting corrosion because aluminum can form a really thin passive oxide film on the surface, making it more resistant to corrosion than steel. Right? So aluminum is lighter than steel, better corrosion resistant than steel. So a lot of application where we do not need too much strength, but we want lightweight corrosion resistance, we would probably choose aluminum. right? Okay, so aluminum has good corrosion resistance in some common environments, including ambient atmosphere, right? So normal atmosphere, it's got good corrosion resistance. But if you put aluminum in seawater, it acts the same way as steel, right? It's vulnerable to seawater, unlike bronze or brass. It's got very good ductility. Aluminum has FCC crystal structure, so it's got very good ductility. You can form it into really, really thin sheets, right? So if you look at the aluminum kitchen foil, it can be formed into really, really thin foil, right? Because it's got really, really good ductility. Okay, so uh, if you've noticed the kitchen foil, right, you have one shiny side and one duller side, right? Um, Maybe you might have wondered why that is, right? So think about it, why that is. I will talk about it out later I will tell you later in the manufacturing class why the kitchen foil have one shiny side and one duller side, right? Aluminum alloys have many grades um, depending on the alloying element that you put in, and you can shape it into different shapes that you want. You can form it using casting to form uh, this housing for the gear in a car. You can form it into alloy wheels, aluminum alloy wheels. You can form it into these different cross section from extrusion to be used in, say, like window frames, etc. Right. So when you start off with aluminum, and you can add in all these alloying elements like zinc, magnesium, copper, manganese, and silicon. Right. So you can mix aluminum and zinc together to form aluminum alloy, aluminum, zinc, magnesium, and to form like aluminum alloys. All these aluminum, copper, magnesium, silicon, aluminum, zinc, magnesium, copper. All these are precipitation hardening alloys, right? So these alloys can form precipitates. Um, you've seen this sort of precipitates in the phase diagram section, right? So you can form small precipitates like this, and this precipitate can increase the strength of our alloys, right? So if you form precipitate like this, it can increase the precipitate. And we'll discuss more on this topic of precipitation strengthening after the midterm, right? But for now, you you have to, well, for now you just have to know that all these aluminum alloys can form precipitates and can increase the strength by precipitation hardening process. Aluminum silicon and aluminum silicon copper, okay, so these alloys are cast alloys, so they will be using they will be used in casting application, because silicon can increase the flow rate of the melt. Copper can reduce the melting point of the melt. So they are very good at casting alloys. Aluminum, magnesium, and aluminum manganese is well, these are used at work hardening alloys. That means these two materials can increase their strength by work hardening, by forming it at low temperature, by cold working it. Right, so these material can form dislocation more easily, and this dislocation can hinder other dislocation to produce higher strength. Next type of material is magnesium alloys, right? Magnesium has really low density of 1.7 gram per centimeter cube. It's one of the lowest, if not the lowest, density in all of engineering metals, right? So it is one of the lightest metal. It is used in application where lightness is important, like the structural frame of aircraft or missiles. Right? Um, okay, it's used in lightweight application like aircraft components. Um, in alloy we use like alloy magnesium alloy wheels are used in racing cars because the magnesium alloys can be really strong, but at the same time very light. Magnesium is relatively soft and has low elastic modulus of 45 gigapascal. So we have to mix in other alloying elements to increase the strength and hardness of aluminum. Right? Uh, Usually we add aluminum, zinc, manganese, silicon, copper, and maybe a little bit of rare earths and zirconium in that. Right? So we can produce a stronger material, a stiffer material, yet light material. Right? Material alloys are typically used as cast alloys because the melting point of magnesium is relatively quite low, so it's easily cast into the shape that you want. Um, Magnesium alloys are used in many components of cars, and there's some magnesium alloy engine block have been used in some high performance vehicles. Right, so you want good performance, you want lightness, right? You want low weight so that the car can move faster, right? So that's why you might choose a magnesium engine block. Magnesium die casting is used for camera body and components in lens, especially higher end um, digital SLR uh, camera, right? So if you are holding a big like Nikon or Canon uh, EOS 1N or whatever, um, those big camera, the frame of those camera are made from magnesium alloys, and you might have some sort of like titanium paneling or sometimes plastic paneling, but the frame are usually made from magnesium alloy for high strength. But the lower end model, the the consumer model and the prosumer model are usually made from aluminum alloys and plastic or just plastic. But the higher end, you have the magnesium frame. Um, Titanium alloys. Titanium alloys have been around for a while now, has been used quite a lot because it's got really high strength comparable to steel. Okay, aluminum alloys, magnesium alloys, you can increase the strength by alloying by precipitation strengthening or whatever, but the strength is not comparable to steel, right? But it's got much lower density, so you can probably increase the thickness of the section so that the overall strength can be comparable to that of steel. But titanium and titanium alloys can have strength very similar, very similar level to the strength of steel, but it's about just a little bit, just a little bit over half the density of steel. So it's a lot lighter, right? It's got high melting point, so it's difficult to cast, but you can use it. You can use it in other methods to form it. Right? It's got high elastic modulus of 100. Well, medium, I would say, like medium to high elastic modulus of 107 gigapascal. Titanium alloys are extremely strong. Like I mentioned, it's as strong as steel. The tensile strength at room temperature can be as high as 1400 megapascal. Which is quite high, high specific strength, right? The specific strength refer to the strength per weight ratio, right? So because it's got as high as high strength as steel, maybe just a little bit less than steel, but because it's got about just half the density of steel. If you take the strength divided by the density of that material, you get specific strength, right? So the specific strength of titanium alloys are very, very high because of the low density, right? Strength divided by density gives you specific strength, right? Because of the low density, you get really high specific strength. Titanium alloys are used in airplane structures, space vehicles, right? So application where you need lightness and strength, surgical implants, uh, uh, petroleum and chemical industry, because you want these material to be compatible with the environment within the body. So in other words, you want it to be inert and do not react too easily, right? So titanium is quite inert because titanium can form a passive oxide film on the surface that makes it really non-reactive, right? So it can be used as surgical implants, and it can be used in petroleum and chemical industries because it doesn't react easily to other components, right? So this is the hip implants. You have uh, the insert that you put on top of the femur. This acetabular cap you put in the hip joint to replace the hip joint, right? So this is the hip replacement surgery. The titanium alloys is used in the compression zone, right? So the fan blade can be made from stainless steel or titanium. The compression zone blades are usually made from titanium, and the turbine blades are usually made from nickel superalloy. Fun fact: this hip joint replacement is made from titanium Ti64, titanium with 6% aluminum and 4% vanadium, right? Sometimes this is called grade 5 titanium, which if you follow the launch of the iPhone last night, the new iPhone Pro and the iPhone Pro Max will start to use titanium as the body of the iPhone Pro and the Pro Max, and they will use grade 5 titanium, which is the same grade as the surgical implant grade, right? Ti64. There was like, I don't know. There was a funny quote, not so funny, but the person who was doing the presentation said that they are using grade 5 titanium alloys, which is stronger than pure titanium. Which to me that sounds funny because of course alloys are stronger than pure metal, right? But you don't even have to say that. So I don't know why she has to say it like that, but it sounded funny to me. Like strange, not like funny, haha, funny, but just strange. Anyway, so if you look at this Boeing 787 Dreamliner, you see the titanium used for about 15%, right? So a lot of that will be in the engine and also the structure, the main structure of the aircraft. Some part like the structure that have to connect to the engine will be made from from titanium, but some part that require really high strength will still need specific type of steel, right? But you can see that 50% is made from composite material. That will save a lot of weight. That will make it really fuel efficient and can fly further. So in aerospace applications for titanium, you can have compressor disc, like so, somewhere around here in the jet engine, like uh, fan blades of aeronautical engines. Landing gear can also be made from titanium alloys, springs, structural component in the fuselage. Right, so you are using titanium because you have a lot of weight savings. Titanium has good fatigue strength. It can be operated at high temperature, so you have operating temperature capability. It's very good corrosion resistant, and it has space saving. Right, space saving in this case is when you compare titanium to aluminum alloys. Right, so to achieve the same to achieve about the same level of strength, you need thicker section for aluminum alloys, right? Uh, because aluminum alloy is not as strong as titanium. So because if you're using aluminum alloys, you need thicker section. When you change to titanium alloy, you can you can reduce the section of the component to be thinner, and by doing that you are saving the space. You can use the space to do something else when you reduce the cross section of the component, right? That's what space saving means. Okay, so this is the Ti64 that I mentioned, titanium 6 aluminum 4 vanadium, right? So this is the uh, most popularly used titanium alloys. It's got high strength. It's used as surgical implants, root canal, hip joint replacement, knee joint replacement, chemical processing equipment, aircraft structure, etc. Okay, so next type of alloys is the super alloys. In the group of super alloys, okay, first of all, we call it super alloys because these materials have very high strength, especially at high temperature. So you have a lot of materials with very high strength, but you have just a handful of materials that have high strength at high temperature. And because of that, we call these materials super alloys because they are very good at high temperature. Right? And these materials are used in aircraft turbine components because they can withstand high temperature, highly oxidizing environments for a long period of time. Right? So the turbine blade is somewhere here. Right? So you have compression zone, you have combustion zone, and you have turbine or exhaust zone of the jet engine, the gas engine. Right? So in this area, you have hot gas coming out from the combustion zone. The gas expand. The gas is very hot after combustion. So in this chamber here, you need a material that can withstand high temperature up to 600, 700 degrees Celsius. And that material has to be very strong at that temperature and um, has to be able to withstand oxidizing environment at that high temperature. So there's only a handful of material that you can choose from. Okay, so that material, those materials are called super alloys, and we can divide super alloys into three groups. We have iron nickel super alloys, nickel super alloys, and cobalt super alloys. Right? We have iron nickel based superalloy, nickel based superalloy, and cobalt based superalloy. And then in these three groups, we can add other alloying elements, especially refractory metals like niobium, molybdenum, tungsten, tantalum. Right? Okay, these are refractory metals. Right? Refractory metals are metals with high melting points, and when you add these refractory metals, metal with high melting point like niobium, molybdenum, tungsten, and tantalum, to an alloy, you will make that alloy stronger at higher temperature. You will make it more able to withstand higher temperature, right? Fun fact: W is a symbol of tungsten, right? But why W? Because in German, tungsten is Wolfram, right? That's why we use this symbol of W, tungsten and Wolfram. Okay, because it was discovered in Germany, I think. I'm not sure about the name of the person who discovered it about 150 years ago. Okay, so when you add refractory material like niobium, molybdenum, tungsten, and tantalum in there, you add chromium and titanium in there as well. These material like chromium and titanium, they can form passive oxide film, so that can help prevent oxidation at high temperature. Right? So these superalloys are super because within themselves they have good properties, but when you add all these alloying elements in there, you make them better. Right? So we have iron nickel based superalloys, nickel based superalloys, right? Rod nickel, cast nickel, and cobalt based superalloys. Okay, so these are the superalloys that have been used for a while now, like Inconel, Incolloy, Rain 80s, Haynes 25, X40. These have been used a lot in power generation application, steam turbine engine, gas turbine engine, right? So you can see that. For example, like iron nickel base, you have mostly iron and nickel. You add in a little bit of molybdenum and you add chromium and titanium, right? For Incolloy as well, you have like mostly nickel and iron. You have chromium, bit of titanium and molybdenum, right? For Rain 80, it's nickel based, so you have a lot of nickel. You have cobalt, molybdenum, tungsten, right? And see that these are the like alloys, right? So you don't have to remember all this, but you have to know that there are three groups: iron nickel based, iron nickel based superalloys, nickel based superalloy, and cobalt based superalloys. And these base material can be modified by adding niobium, molybdenum, tungsten, tantalum. These metals are called refractory metals. These metals can withstand high temperature. They have high melting points. And when you add these metals to something else, you make them stronger at higher temperature. But these metals are expensive. Right? You add chromium and titanium, also will improve their high temperature properties and also will improve the anti-oxidizing property as well.